morning. Let's get started. So in the last lecture, we showed you how to go digital. Okay, the fact that going digital had some key benefits for us. And what we'll do today is go inside the digital gate. Let's do a quick review. So we began life by observing nature. He said, "Whew, those Maxwell's equations are tough. Let's simplify our lives by discretizing or lumping matter." So we got the lumped circuit abstraction. Then we said, we have this noise problem here. So in order to be able to handle that, let's do some more discretization, some more lumping. So we said, let's discretize values and deal with two levels, a high and a low. That's where the binary voltage levels come up, a high level and a low level. And then we said that in discretizing it, we have to make some assumptions. We have to impose some constraints on ourselves. Just as with the lumped matter discipline, we imposed a couple of constraints in going from the continuous matter world to the lumped matter world. Similarly, we have to impose some discipline on ourselves, some constraints on ourselves in going from the continuous value regime to the digital value regime. And that discipline is called the static discipline. And what the static discipline says is that if you have senders and receivers in a digital system, then they all need to adhere to some standard. Okay? So if I was a sender, I had to adhere to some tough output standards. Okay? I had to be sure to ship values that exceeded some high voltage threshold. And if I was sending a low value, I had to make sure my values were lower than some output low voltage threshold. Okay, similarly, if I was a receiver, then I had to guarantee to recognize as a 1 all voltages that were above some input high voltage threshold. And similarly, I had to guarantee to recognize as a 0 voltages that were below some input low voltage threshold. Okay? So provided senders and receivers in a system adhered to these voltage levels, to this discipline, then they would all very comfortably work correctly in a digital system. Then we also said that once we deal with such values, once we deal with digital values, we can now postulate a bunch of digital elements that process these values in a manner very reminiscent of our analog circuits, where we had analog signals, and you've already learned how to process analog signals. You've learned about resistor dividers and so on and so forth. You feed in an analog signal and you get an output analog signal as well. Now, here, the resistor in the analog domain, elements like resistors and voltage sources were the symbols that you dealt with. Here, in the digital domain, the primitive elements that we will be using are called gates. Okay, as one example, this is called the NAND gate. Okay, so we looked at the AND gate in the previous lecture. This is an example of another gate called the NAND gate. The NAND gate has the following truth table. Two inputs A and B, and then output C. And the NAND gate works as follows. The output In English, I can describe its properties as the output is a high at all times when at least one of these inputs is a low value. Okay? So it's high whenever at least one input is a low. So it's high here, it's high here, oops, it's high here, and when, oops, and when both inputs are a high, the output is a low. This is a NAND gate. Notice that these are exactly complementary to the AND gate. The AND gate outputs were 0, 0, 0, 1. Okay? And the AND gate symbol looked like this. In general, notice that this little bubble here, it's called a bubble, that bubble implies a negation, an inversion. Okay? So you take the AND gate, invert the output, and negate the output, and you get the NAND gate. Okay, so these elements are combinational gates, and in combinational gates, they adhere to two properties. One is that they must satisfy the static discipline. Okay, all the systems, all the elements in our repertoire in the digital domain need to satisfy the static discipline. And the properties of a combinational gate are that its outputs are a function of inputs alone. In other words, it doesn't store any state or doesn't store any history inside it. You can figure out its output just by looking at the inputs at that instant. Okay? Think of it as a completely transparent entity where its output reflects some function of the inputs at every instant of time. Okay. So I'll show you an example digital circuit. So much as I could interconnect resistors and voltage sources and current sources to build analog circuits, I can now build digital circuits using primitive elements such as these. So for example, I could build a simple circuit that looked like this. Two inputs, A and B here. I get an output, and I feed that to another NAND gate. Another input C. This device is called an inverter. The inverter simply flips the sense of the input. So if C is a 1, output is a 0. If C is a 0, the output becomes a 1. It's an inverter. Simply inverts its input. Yet another primitive device. And this is my output, D. So there are 3 gates in this design. Okay? And I can quickly write down what the output looks like using some very simple Boolean algebra, or dealing with Boolean values here. So for an AND gate, the output is A and B. Remember, dot is a short form for AND. But there's a negation, inversion. So I represent inversions with a bar. Okay, so my output is A dot B bar. This is C here. So this is my output, C bar. Okay? And this is a NAND gate. So it takes one input, A dot B, takes the second input, C bar, and ANDs those and inverts them. Okay? So that's the output. So there are 3 gates in this example. So you can think of building very complicated circuits containing large numbers of gates. In fact, the microprocessors that you use in your laptop contain a large number of gates. So can someone guess how many gates are in the Pentium 4? Roughly, to within approximate. How many gates in a Pentium 4? 40 million. 40 million. Pretty close. How many? It's going up. Ooh. So in the Pentium 4, you have on the order of 20 million gates. Okay? 20 million gates in the Pentium 4. So, and life begins in 002. Here you learn about onesies and twosies, and in the real world, you will be dealing with, tens of millions of gates. So this is for the Pentium 4. My research group at Laboratory for Computer Science built a chip called the raw chip, and this chip has 3 million gates. Okay? And so there are several undergraduate students involved in this project in their third year, and they're beginning to deal with millions of gates. So the key thing to remember is that 002 provides the foundations where you make the switch from the analog signal to the digital signal, or from continuous matter to discrete to lumped matter, and learn about the foundations of these primitive elements. Okay? And by the end of this course, you will begin dealing with small systems, analog systems that contain on the order of 10 to 20 primitive elements. You will also begin dealing with small digital systems that contain tens of gates. Okay, in your final project, you will build a mixed signal circuit involving an audio playback system. You'll have digital data stored in a memory chip, and you will build a circuit to extract that data, filter it, and then convert it to the analog domain, and then play it on a set of speakers. And that has on the order of about 50 to 100 primitive elements. So by the end of 002, you'll have learned to deal with hundreds of elements. And then you will take other courses like 004 and so on, where you'll then make the leap from learn further abstractions that will take you from such systems to systems with millions of gates. Okay? So the key is to manage the complexity of dealing with millions of gates, it's all about abstractions. Okay? You have to build abstractions on top of abstractions so you can deal with complexity. So here, the rest of EECS will take you from 3 gates to 20 million gates and software systems that operate on 20 million gates or whatever. So there's still a ways to go. Lorenzo, our friend, has gone to bring a demonstration that we forgot to bring today. That will show you that little digital circuit in a mock-up form. Okay, so what's today's lecture about? Today's lecture is going to be about what's inside a gate. Okay? How to build a gate. Once you build a gate, you can then put millions of them into computer systems or analog systems or other sorts of systems. And what we'll do here is understand what's inside this abstraction. This is an abstract element that looks like a little circle and a line with some stuff inside it, with some properties. Okay? But someone's got to build that. Okay? It doesn't come from nature. You don't go and harvest gates from trees. You've got to go build that, and someone's got to do that. So what we'll learn here is how do we go about building a gate? And here you will see practically how do you deal with voltage thresholds that satisfy a given static discipline. So before I jump into building a gate, let me try to build up some intuition. Okay? As is my usual practice, I'd love to get you to build some intuition as to how to build a gate. And then we'll go through the mechanics of doing it. So to build intuition, let me show you a analogous situation in fluids. So let's say I have a cauldron of water. This is like a power supply. And I need to feed this fluid down at some output source. And what I do in the middle is put in a couple of taps. Faucets, all right? And so what do these guys do? So under what condition do you have fluid flow out of the tube at the other end? You will have fluid flow if, so let me call this A and B. Okay, so if A is on and B is on, okay, then C has water. Otherwise, if both A and B are not on, then C has no water. Okay, so this is already beginning to sound like a AND gate, correct? Where if you get water only if A and B are both turned on. So we're going to use this insight, okay, stream of some flow, and I put things to obstruct the flow, and when both the obstructions are lifted, I get the output. I'm going to use that intuition to build a AND gate. Similarly, I could build a system that allows me to build the following structure. So in this scenario, let me call this the signals A and B here. And in this situation, under what conditions, provided the power supply has water, under what conditions do I get water out? In this situation, it is I get water if A or B are turned on. Okay? So it doesn't, I don't need to turn both A and B on. If either one of them is on, I'm going to get fluid flow here. So this will help us build the insight to build the OR gate. Okay. So that's a analogy involving items we see in everyday life. Let me now move into the electrical domain. In the electrical domain, my analogy would be something like this. Let's say I have a power supply, and I have two switches, A and B, and I build a little circuit that connects this voltage source across the bulb using a couple of switches. In this case, the bulb is on if both switches A and B are on. Okay, my bulb turns on. If I switch either one of them off, my bulb turns off. So notice that I can begin implementing things like this if I had this element. Okay, I have sources already. Okay, I know how to deal with bulbs. I model them as resistors. So I need to do something about this new element called a switch. Okay, so let me build an abstract device. I'll tell you how to do that in real life in a second. So if I had a switch, I could build things like this. I could put switches in series in a circuit and get myself something that looks like a AND function. So let me go ahead and build an equivalent circuit for a switch. So a switch has a couple of terminals here, and I have a control. Okay, switches have a control, and they have a pair of terminals. And the equivalent circuit for this looks like this. This is for my switch. So when control is a 0, then my switch is open. Okay, to give me an open circuit in the circuit that I've shown you here. And by the same token, if my control is a 1, then my control is a 1, then I have a connection between in and out, and this is a short circuit. So in other words, if my switch has 0 at its control, and I'll talk about how to get that, I have an open circuit, and if it's a 1, then I have a short circuit. Okay, this is my switch going on and off. Now, in traditional switches, mechanical pressure is my control signal. Okay, if I apply mechanical pressure, my switch could turn on. And if I take away the mechanical pressure, then I could get an off situation. So for now, let's imagine. Let's imagine that we have a switch. Okay, I still haven't told you how I am going to get a switch in real life. Let's imagine you have a switch. It's a 3-terminal device. There's a control thingamajig coming in, input and an output. So let's build the following little circuit containing a switch. So what I'm going to do, I'm going to take a resistance RL and plug it in here. And connect my power supply like so. So the little circuit that I build has a resistor, and I connect the switch in this pattern, and I get a VS. Well, Laurent, you can set that up there if you like. Okay. No problem. So I get a VS here. Now, a couple of lectures ago, I told you that 6002, and for that matter, 004 and many of our other courses, deal with combinations of elements. And we often deal with the same kinds of combinations again and again and again. Okay? We see the same sorts of patterns happening, and we need to begin to learn to identify these patterns. This is an incredibly common pattern. Okay? You'll see this pattern more times in 6002 than any other pattern, I promise you. Okay? A power supply connected to a resistor and connected to a couple of terminals of some interesting device. Okay? I promise you there'll be at least one such pattern on the quiz, for example. These patterns are incredibly common. Okay? So let's take a look at the interesting properties of this pattern. Since this pattern occurs so commonly, I am going to create a short form. I have already created a short form, which is this ground node here. By putting grounds here, all I'm really saying is that these two, there's a wire connecting these two, and that's my ground. Okay, so I already have a short form here. My second short form is when I connect a power supply to a node, then what I'm going to do is come up with yet another short form that looks like this. An up arrow with the voltage written there. This symbol simply says that this node is connected to a power supply with voltage, or a voltage source with voltage Vs. Okay? So I just have come up with a slightly simpler representation for the little pattern that I have. Okay, now let's take a look at the properties of this little system. Let's first look at what happens when C is 0. When C is 0, let me draw the equivalent circuit for this using the open circuit out there. That's what I get. Okay? So when C is 0, if Vs is a high voltage, let's say 5 volts, what do you expect at the output if C is a 0? Simple enough. Okay, this voltage Vs appears at V out because this is an open circuit here. Remember, RL and this little device form a voltage divider, but since it's an open circuit, its resistance is infinity, and so therefore, in this resistive divider, all the voltage falls across this open circuit. Okay? So in this case, V out is a 1, or a high. We get a high voltage. So let's take a look at what happens when C is a 1. In this situation, I have my RL. That's what I have. It's a short circuit at the switch, and C is a 1. So what's the voltage V out in this case? Well, not surprisingly, since I've shorted this node to ground, the voltage at this point is 0. Okay? So I get if I have low voltages corresponding to logical zeros, that corresponds to a 0. So I can build a simple truth table for C and my output and use logical symbols here. So when C is a 0, I get a high at the output. And when C is 1, I get a low at the output. Okay, have you seen a device that behaves like this so far? That's a little inverter. That's the exact behavior of our inverter. Okay? So this thing that I've written here is a truth table for an inverter. So notice, with just a simple little switch and a resistor, I have managed to build an inverter. Before I go on, I guess we have some things to show you. And let me pause for a couple seconds and do that. First of all, what I want to show you is the following idea. So as I was preparing for this lecture last night, I said, here I am telling, telling the 6002 gang that, you need to learn about analog circuits and resistors and all of that stuff. And you also need to learn about digital systems and all of that stuff. And I said, because these two are very commonplace and oftentimes they occur together. So I said, well, if I really believe in my own BS, then there should be something around me. There should be something around me where I can find both of them instantaneously. So I said, let me do the following Gedanken experiment. Let me close my eyes and reach out and see what I touch. So I closed my eyes, reached out, and guess what? I touched the lowly mouse. Okay. The mouse. So I said, okay. So I said, let me see what's inside the mouse. Okay, and if I believe in my own BS, we should find analog little components and digital components in there, right? So let's see what's inside the mouse. All right, there we go. Don't try this at home, as with many other things we do in lecture. Come on. Show me what I want to see. Okay, here we go. Okay, not bad. Okay, let me show you what we have here in this poor shattered mouse. So you should recognize, that's my finger, silly. So you should recognize this little mouse, or this little resistor here. The thing with the little bands out there, that's a, oh, here we go. Let me use this. So that's a resistor. Okay, and you'll see capacitors in about 4 weeks. That's a capacitor. And there's a digital IC here. That's a digital IC. That contains a bunch of gates inside it. So, this mouse has not made a liar out of me. So what I just showed you was a little device that we use in everyday life that has both analog components and digital components. A large number of the devices that we use in daily life are this way. Okay, you do the same thing to your laptop. You can go try it out, and you will find, a bunch of analog components and a bunch of digital components, and you really, really need to understand the whole caboodle here. Okay, so let me show you a fun little demo involving gates. Now, I want you to be very careful here. Lots of caveats here. So if your grandmother asks you, how big is a gate, don't say this big. So this is how big gates used to be, I would say, when they were first invented. Okay, when they built gates out of discrete vacuum tubes and so on, this is how big a gate used to be. So this is roughly that big. Today, in a chip, in a small VLSI, very large scale integrated circuit in a chip, which is about 1 centimeter on the side, how many gates do you think I can fit in a thumbnail sized chip? Any guesses? With today's technology, how many gates can I fit on a chip? It has to be more than 1 million, because I just told you the Pentium 4 was 20 million. And that was a year ago. How many? 40 million is a good guess. So on the order of 40 to 80 million gates in a 1 square centimeter. Intel just announced that they'll be shipping a 1 billion, a chip containing 1 billion switches. Okay, remember, this whole thing is a gate, right? Inverter, a resistor, and a switch. This thing is a switch. So Intel's going to be shipping something containing 1 billion of those little elements. Okay, just keep those large numbers in mind. So here's a little circuit that I showed you here. A, B, the NAND gate at the output, and the inverter. Okay? So this output is going to be 1 whenever either A or B is off. Okay, so the output is a 1 in this case when both A and B are off. I turn A to 1, output is still a 1. So the moment I turn both of these inputs to a 1, these are 1s, the output goes to 0. That's behavior of a NAND gate. Okay, if I switch any one of the inputs to a 0, the output should go to a 1. Okay? Similarly, for the inverter here, when the output is a 0, input's a 0, the output's a 1. And when I switch it, so should the output. Okay, now imagine a circuit, a little chip, containing billions of these devices. Okay? And just imagine all of these 1s and 0s flying around. So one simple switch in the input, like a click of a keystroke, could actually cause 1 billion signals in your circuit to be flipping around. Okay, and that causes some fun stuff to happen, which we will learn about a few months from now. But for now, that's a quick show of a little circuit that looks like that. Okay? Let me go back to talking about building other types of gates. So that was an inverter. Okay, so now you know. So you're almost halfway to being able to build a Pentium 4. You've come all the way from nature to gates. Okay, and so and the Pentium 4 contains 20 million of them. So you now know how gates are built. So let's look at, that's an inverter. Let's look at how we can build other gates, other forms of gates. So to build another gate, let me do this. How about this pattern? If I build a pattern like this with A and B coming in here, and I put 2 switches with their inputs in and out. So 2 switches in series. Okay? Let's write down the truth table for what this looks like. So let's see. When A and B are both 0, what should the output be? These are both off. So the output is directly Vs, which is a high. When either of these switches is off, 0, 1 or 1, 0, if either switch is off, then this node is cut off from ground. Okay, there is no current flowing here. Okay, so this entire voltage drops across this infinite resistance here, and so I get 1s at the output as well. So if both switches are on, what happens? If both A and B are on, then I get a short circuit to ground, and my output is a 0. So can someone tell me what gate this is? Awesome. We've just built an AND gate. This is unbelievable. 5 lectures, and you already come all the way from nature to the primitive building blocks of microprocessors. Pretty amazing. Okay, so what about this one here? What's this? I haven't told you this before, but if an AND gate becomes an AND gate, this is kind of an OR arrangement. What should an OR become? It's all completely logical. Okay? So you can go home and practice a truth table for this. A, B, and C. Okay? I'll just fill in one of the rows. So in this particular situation, if both A and B are 0, if A is 0 and B is 0, both the switches are off. So it's as if this little sucker here is cut off from ground, and Vs falls across from C to ground here, and the output is a 1. Okay? So on and so forth. So I can build other interesting forms of gates. So let's say I build something that looks like this. So build something like this. So you can write the truth table for this, or you can look at this and write down the function that this one supports. So notice that this output here is going to be a high only when both of these are not connected to ground. Okay? And if you stare at it some more, the function this one presents, this is my AND function. So suppose this one didn't exist, that would be my AND function. Okay? But because this one exists, that's in an OR configuration, and so I get a C. Okay? And so because of that, I get something that looks like this. So this is my A dot B. This is my plus because of a parallel shunt here. And ultimately, this causes an inversion in this gate. So our primitive pattern has a generic inversion built into the output. Okay, that is why we commonly end up building NAND gates and NOR gates and so on as the simplest gates. We don't build AND gates and OR gates. How can I convert this one to a AND gate? Anybody? Put an inverter on the output. So what I can do is take this little sucker here, put an inverter here, and I get an AND gate. Okay, so the real primitives in circuits tend to be NANDs and NORs. Okay. So the real practical among you should be saying at this point, all right, I buy this. If there existed a switch, okay, I know exactly how to go from nature to building Pentium 4s. If there exists a switch. So the obvious next step for me is to show you a switch, a physical switch device. And to introduce a switch device, let me show you a 3-terminal element. Remember, the switch has 3 terminals, an input, output, and something called the control, C. So I'm going to introduce a new device called, a new primitive element called a MOSFET device. Okay? MOSFET stands for metal oxide semiconductor field effect transistor. Okay? This is shortened to FET or transistor. Okay, and I'm going to build a switch and show you that this works like a switch. And before I do that, actually let me do that first, then I'll show you something else. So this device has the following symbol. It has a terminal called the gate, the drain, and the source. Gate, drain, and source. 3 terminals. Okay? This is the primitive element that forms virtually every electronic component built today. Okay, this is the foundation of the universe. So this little MOSFET device, we can look at how it behaves. I'll show you this thing on the screen in a second. But this guy behaves very much like this device I was postulating earlier. Okay, let's take a look at this device on the scope. To do so, let me label some voltages and currents. So let me label this voltage as VDS. Let me label this voltage as VGS, between the gate and the source. And let me label the current coming into this node IG. Okay? In this device, the physical device that I'm going to show you, the current going into the gate is always 0. Okay? So IG is always going to be 0 for 6002. Okay? In real life, there is some leakage and so on, but in 6002, for now, we deal with a very simple abstract model. IG is 0. Okay? And let me label the current here as IDS. Okay, to be corrected by nomenclature, the current into node D should be labeled ID, but because IG is 0, ID flows out through the source as well, so I'll simply call it IDS. just so that I can show that VDS and IDS are the two the voltages and currents that I am going to deal with. So that's my little device here. And notice that the source terminal is common. I use the source both for the control GS, and I use the source for the drain as well. So you can view this as your input, view this as out, and you can view this, if you like, as the control, okay, abstractly. So let me show you a plot of how this behaves. To understand how it behaves, I can draw an equivalent circuit for it. And so in this particular situation, if its behavior is characterized by the voltage applied to VGS, much like the control on the switch, VGS is my control. So when VGS is 0, if VGS is greater than or equal to some threshold voltage VT, okay, so if VGS, the voltage applied here, is greater than some voltage, VT, a threshold voltage, or the pressure on the switch is greater than some threshold pressure, then this guy behaves like a short circuit. Okay, this is IDS, this is my drain, and this is my source. So if the voltage applied between the gate and the source is higher than some threshold, then this behaves like a short circuit. Similarly, if the voltage VGS is less than some threshold VT, then in that situation, I get an open circuit. And when I have an open circuit between D and S, then the current IDS is going to be 0. So this is the idealized model. And this idealized model is called the switch model of the MOSFET. The switch model of the, or the S model of the MOSFET. Now, if you want to see the internals of the MOSFET, I won't cover that in lecture or recitation. You can look at the section, I believe, section 6.7 of the course notes. Okay, that has the internal structure of the MOSFET and how you physically construct such a device. So what I can do here, step back and stare at the device for a second or two, and what it says is that if I apply a lot of pressure, if VGS is greater than a threshold VT, then I get a short circuit here. Just like my switch, just when in doubt, think faucet. When you put pressure on the faucet, think of this as closing, and when I open it, when VGS goes less than VT, less than a threshold, I take off the pressure, then it becomes an open circuit. So I can plot the following. Much like I plotted the IV characteristics of two terminal elements, I can plot the IV characteristics of this three-terminal element in the following way. I can focus on two terminals and look at the look at VDS and IDS for that terminal pair, okay, and draw the curves for how it will behave as I change VGS that I applied. So what I'm going to show you is that if VGS is less than a threshold, then this behaves like a open circuit. So no matter what the voltage is, the current is 0. Similarly, if VGS greater than or equal to some threshold voltage, then I get the behavior IV curve of a short circuit where the current can be anything and controlled by external forces like in any short circuit. Okay? So let me show you on the screen. Lorenzo has kindly put the graph up already. So I'm showing the IV curve of a switch. Notice that when VGS is greater than VT, greater than a threshold, I get the vertical line corresponding to a short circuit. Is it this one? Yes, this one. There we go. So what I'm going to do here is I'm going to reduce VGS to below VT. Okay, what should you see happening? The curve from being a short circuit should hammer down to becoming an open circuit. Okay, that's the curve for an open circuit as I drew out there for you. VGS, pressure ain't enough. Lots of pressure, boom, it's a short circuit. Okay, I really like to think of this pressure analogy if I get confused. whenever I look at a MOS transistor and I need to look at VGS and so on, I always think, when VGS is greater than VT, lots of pressure on a switch, it turns on. Okay? Just remember that, and then you won't forget this VGS thing here. So that's the behavior of a switch, and so voila, there's our switch. Okay, so I've given you a three-terminal element that is a switch that is controlled like a mechanical switch. So I can build if I replace so this was my switch earlier, and what I can do is replace this with my MOSFET, and that's what I get. Okay, and I won't bother showing you this is your inverter. All I've done is replace the abstract switch with a physical switch, which behaves as shown in the graph out there. And so I apply an input here, and I take the output here. Okay, so at 6002, you can look at this and say, aha, that is an inverter. When you go to 004, what you will do is build this triangle and a circle around it, and you will ignore what's inside. And just look at that. Okay? So in 002, we showed you that the internals look like a pattern with a MOSFET and a resistor, but it's really the abstract inverter looking in from the outside. So this is going to close the loop on inside a digital gate, and this was inside your little inverter with a resistor and a switch. Let me continue with this for a little longer here. And do something that we like to do a lot, which is plot what are called input-output curves. So let's say the voltage applied here is V in, and let's call this V out. Let's plot the V in. For fun, let's plot a V in versus V out for this inverter. Okay? So when the input is a 0, let's say VT is 1 volt for the inverter. The threshold voltage is 1 volt. The threshold pressure is 1 volt. So when the input is a 0, and let's say Vs is 5 volts. So when the input is a 0, this guy is turned off. Okay, so what's the output? What's the output voltage? If this is turned off, what's the output voltage? It's the supply. The supply directly shows up here, and so as long as the input is 0, the output is at 5 volts. And this is true until the input reaches 1 volt. As long as the input is less than 1 volt, my output stays high. And then when my input exceeds or hits 1 volt, then at that point, the switch turns on, and the MOSFET turns on and shorts the output to ground, in which case, boom, this is what I get. Okay? And then, no matter how much I increase the input, my switch stays on, and the output follows a 0 volts at the output. So this is my V in versus V out curve for the inverter. Okay. One of the interesting things that we do a lot is see whether this satisfies some voltage threshold. So let's say I have a VOL of 0.5 volts, VOH of 4.5, VIL of 0.9, and VIH of 4.1 volts. Okay? So VOL says in its low value is the output less than 0.5. Yep. Output less than 0.5. In its high, is it more than 4.5? Yep. It's more than 4.5. Does it recognize all values below VIL as a low input? Yep. So anything below 0.9 or 1 for that matter is viewed as a low. That's good. So these pass. And high, anything above 4.1, is that treated as a high? Yes. So anything above 4.1 is treated as a high, and the output goes low. Okay? So therefore, this inverter that I've designed for you here satisfies the static discipline, and this inverter can be used in circuits that conform, or other devices that conform to this value here. In your recitation, you will look at a slightly more detailed model of the switch, where the switch behaves like a resistor. Okay.